Whenever you encounter a subspace in linear algebra, there's two natural questions that are going to come to mind. The first one is, what's the dimension of this subspace? Right? That's probably going to be the first question that you want to ask. And that's going to lead you actually to the second question, because what do you need to find the dimension of a subspace? You need to find a basis for it so that you can count the vectors, and then upon counting the vectors in a basis, that will tell you what the dimension is. So that leads to the second question. How do you get your hands on a basis for this subspace? Now, in the case of a row space, this fact answers that question. So if you want to find a basis for the row space of some matrix A, all you have to do is just row reduce it. You don't need to go all the way to reduced row echelon form, but you certainly can if you want. But just row echelon form is good enough. So just row reduce the matrix until it is in row echelon form. And then once you've done that, just take the non-zero rows. And that'll give you a basis for the row space of the original matrix as well. So let's look at an example here. And in this example, we're asked to find the dimension of, first of all, the row space and of the column space, and in regards to this particular matrix. So you've got a 4x6 matrix. Okay, well, let's start with the column space before we get carried away here. Do you remember how to find the basis, or find a basis, I should say, for the column space of a matrix? You just want to take the pivot columns, right? And how do you find the pivot columns of a matrix? Well, you're going to have to row reduce it. You're going to have to figure out where in reduced row echelon form the leading ones are going to be. Or equivalently, if you can get away with just going to row echelon form as well. If you row reduce a matrix just to it until it's in row echelon form, and then identify which of the columns contain leading entries, that will also tell you what the pivot columns are. So my point here is that in order to figure out the dimension of the column space, you're going to need to row reduce the matrix to at least row echelon form. When you want to find a basis for the row space of that same matrix A, you're also going to have to row reduce the matrix. But the good news is you don't have to do it twice. So if you do the work once, you can use it to identify a basis for both the row space and the column space. So in this example, you can see the work has already started for us, just to save a bit of time to keep this video from getting too long. Some work has been done. Let me just put a little annotation here. You have to do some row reduction here. But you can check for yourself, if you like, that this is indeed a row echelon form of the matrix A that we were given in the question. So if you want to figure out a basis for the row space of A, you just need to look at the row echelon form. And then we'll say, okay, here's a non-zero row, here's a non-zero row, and here's a non-zero row. And those three vectors, if you treat those three rows, I should say, if you treat them as vectors, they'll give you a basis for the row space. So let's start with that. Let me erase these because I think they're covering up a little bit too much information. Okay, so let me say that I'll say B, and I'll say the set containing, so the first vector is 1, 3, 4, -2, 5, 4. Second vector is 0, 0, 1, 3, -2. Oh, that kind of looks like subtraction. -2, 6. This is why I don't really care for writing vectors in row form. But when you're talking about a basis for a row space, it's quite common to write the vectors as row vectors. But if you want to write them as column vectors, I wouldn't fault you for doing it. They're easier to read, and then you have the added luxury of not using almost an entire, look at this, I almost went off the page just from writing down 3 vectors. Like I barely fit that in on one line. And if I had had 4 vectors with 6 coordinates, I would have ran out of space. So for that reason, feel free to write these as column vectors if you prefer. I just don't want to confuse anyone, and I want to make it a little bit easier to recognize the fact that these vectors came from rows of this matrix. Okay, so that is a basis for the row space of A. Now, I'm going to say B1 here because we're going to talk about another basis in the same problem, and I don't want the two to get mixed up. I don't want to use the same symbol to mean 2 different things. That's a bad practice in mathematics. So let's say now B2, and then we can say this is going to be a basis for the column space of A. Okay, so how do we get the column space? Well, we've already row reduced the matrix. You can figure out which of the columns are going to be the pivot columns. We've got a leading one in column 1, column 3, and column 5. So that means we're going to go back to the original matrix, column 1, column 3, and column 5. Those are going to be, well, those are the pivot columns of the matrix A. So they are going to form a basis. When you treat them as vectors, they're going to form a basis for the column space of A. So we want the first column of A, the second column, or the third column of A, sorry, 4, 9, 9, -4, and then the fifth column of A. 5, 8, 9, oops, 5, 8, 9, -5. So, and just to clarify, the reason for that is because column 1, column 3, and column 5 are the pivot columns, right? And that's because of the leading ones in this row echelon form. Those leading entries tell you which columns are pivot columns. Okay, so this is now a basis for the column space. So pay really close attention. There's a major difference in what happened here. Okay, so if I give you a matrix, let's say you're in a situation like this. I give you a matrix, any matrix at all, and I say, okay, I want a basis for the row space, and I also want a basis for the column space. Okay, go find it. And then you go and you do the work. The first thing you're going to do is you're going to take the matrix that I give you and you're going to row reduce it and make sure you get it into row echelon form. Now, once you get to that point, then what are you going to do? You're going to take the rows of the row echelon, you're going to take the rows of the row echelon form matrix that you just obtained, and you're going to put those together into a basis for the row space. A common error that people make is when they go to find a basis for the column space, then they take these columns. But that won't give you a basis for the column space of the original matrix. It will give you a basis for the column space of this new matrix, but this isn't the same matrix, right? It's the row reduced version. It's a row echelon form of the original matrix A, but it's not the same matrix. So when you're getting a basis for the row space, you take the rows from the reduced version. I don't go back up and take those 3 corresponding rows up here. That would not work. But then when I want a basis for the column space, I do have to go back and take the corresponding columns from the original matrix. So there's a major difference in your procedure there if you're trying to find a basis for the row space or for the column space. Okay, but now we weren't asked for bases, were we? We were asked to find the dimension. So let's do that. And because we found the bases, we've found a basis for the row space and a basis for the column space. I'm trying to break the habit of saying the, because there's many bases for any subspace, right? Once we've found bases, we just need to count the vectors. So the dimension of the row space of A is what? Well, just count the vectors. You got 1, 2, 3. So the dimension of the row space is 3. What about the dimension of the column space? Well, count the basis vectors. 1, 2, 3. There's 3 vectors in our basis for the column space today. So that means that the dimension of the column space is also 3. So this example is intended to serve multiple purposes. First of all, I mean, at first glance, it's an example of how you can find the dimension of the row space and the column space of a matrix. But it's also an example of how you can find a basis for the row space and a basis for the column space of any matrix. Okay, so notice that we got 3 for both of these. They're both 3. Is that a coincidence? And the answer is no. Why not? Well, remember, to get a basis for a column space, you need to count the pivot column, or you need to take the pivot columns of the matrix. Well, how do you determine the pivot columns? You row reduce the matrix and figure out where the leading entries are. Right? And how many leading entries are there going to be? There's going to be 1 leading entry for each of the non-zero rows of the row echelon form of your matrix. So we had 3 leading entries, which corresponded to 3 non-zero rows. You can see the correspondence between non-zero rows of the row echelon form matrix and pivot columns of the original matrix. There's a one-to-one correspondence there. So for that reason, they will always be the same. If I change the matrix, I might change the dimension of the row space to something else, but then the dimension of the column space would change accordingly as well. And because of that, we can do the following. So for any matrix, we can define what's called its rank. And the rank of a matrix is, well, you can define it in two different ways. Oops, I'll write it differently. So it's defined, well, first of all, how do you write it? The notation, just like with a lot of the terms we're defining lately, you just write the word rank and then put the matrix in brackets afterwards. But what it's defined to be is the dimension of the row space. But based on what I just said, it's also equal to the dimension of the column space. So if I give you a matrix and I ask you to find its rank, you can figure out the dimension of the row space, or you can also figure out the dimension of the column space. It makes no difference. You'll get the same value. So let's summarize it this way. The row space and column space are always going to be equal. So whatever that column or whatever that common value is, that's what you assign to the rank of a matrix. Now the next thing I'll mention is just the rank theorem. And this is a really nice theorem in the sense that it's very simple to write down. But it depends on a lot of the work we've done leading up to this point and a lot of the things we've constructed. But it's very brief to write down. And that's kind of part of its beauty, is in its simplicity. But this is called the rank theorem. And what it tells you is that if you have any matrix A, notice that's all we need to start off with in the background to state this theorem. You don't have to start off by saying, let this be a subspace and let this be a basis for that subspace, and a lot of the theorems have a lot of complicated assumptions, but this one doesn't. Just start with any matrix. It doesn't have to be square, just m by n matrix, the most general matrix you can ever talk about, right? And here's what the rank theorem tells you. It says that if you add the rank of that matrix to its nullity, you're always going to get the number of columns. Okay, so remember, n comes from the dimensions of the matrix. So the rank of A and the nullity of A will always add up to the number of columns of the matrix A.